Hi class, this is Professor Dave, and this is a video on measures of spread of a set of data. And the measures of spread that we'll look at is the range, standard deviation, and variance. Standard deviation is a measure of spread or a measure of variation in a set of data. Okay, so variation is very important. Variation is all around us. Some examples are if you own stocks, how much does their value vary? Okay, same with your net worth. When you have stocks, houses, everything, how much does your net worth vary? Also, production times. If you want to produce or make something, like even build a house, you need to build a foundation. How long will the foundation take, and how much can that vary? Compound it with all the other variations. How long does it take to build a house? A year? Some take a year and a half. How much variation is very important financially and for your own planning. And also, if your job is a salesperson, for example, a real estate salesperson, how much does your salary vary from month to month? How much do you have to put away? How much can you expect? How about from year to year? All those things are important, so we have to study variation. And standard deviation is our measure of how much variation there is in data, in a data set. Okay, but for the first one is range, very simple one. It's really the highest value minus the lowest value. So if you have this data 10, 12, all the way up to 74, the range is officially 74 minus 10 or 64. But it's very often referred to as the ranges from 10 to 74, and that's completely fair as well. But officially it's highest value minus the lowest value for a single value. Okay, but the real measure of spread of a set of data is standard deviation, and that's really its definition. It's a measure of spread of a set of data, and that's the key thing to know. Four main parameters in statistics is the mean, median, proportion, and standard deviation. The standard deviation measures the spread in a set of data. Okay, so the formula for sample standard deviation, in statistics we assume things are samples. The whole field of statistics is because we sample. So we mostly work with sample standard deviation. Okay, and that formula is the sum of the values minus the mean, those quantities squared, sum them all up. This is a sigma, mean sum, divided by the sample size minus 1, and taking the square root, making the original units. Those would be square units, and bring them back to the original units. That's how you calculate a standard deviation. If you have the whole population, you can divide by the whole population size. But this is how we do it for the sample. Okay, and the variance is just the standard deviation squared. Same formula, just take away the square root. So that's all it is. All right, so let's do an example. Let's say we have a simple set of data, 1, 2, 3, 4, and 5. So let's calculate the standard deviation using this formula. So what we need is the mean. So the mean is clearly 3, the one in the middle, and it's incremental, so that makes sense. It's where it would average or balance the set of data. But the way we calculate it is x bar is the sum. Again, these are the sum of the x's divided by n. So we sum up all these, and we divide by n, and we have 3. So now we need the x minus x bars, x minus the mean. So the first one is the mean is 3. So we have 1 minus 3 or minus 2, x minus the mean. 2, these are our data values, x is 1, 2, 3, 4, 5. So here the 1, 2, 3, 4, 5 minus the means. So 2 minus 3 is minus 1, 3 minus 3 is 0, 4 minus 3 is 1, and 5 minus 3 is 2. Now we square that. Minus 2 squared is 4, minus 1 squared is 1, 0, 0. 1 squared is 1, 2 squared is 4, and then we sum up all these right here, the sum of those. So 4 plus 1 plus 0 plus 1 plus 4, 4 plus 1 plus 0 plus 1 plus 4, it's equal to 10. The sample size is 5, so n is 5. 5 minus 1 is 4. That's the square root of 2.5, which is about 1.58. And the variance, which is just the standard deviation squared, to get rid of the square root or squaring this, we get it's equal to 2.5. or 10 divided by 4. So that's the variance and the standard deviation. Okay, that's how we calculate it, but what does it mean? That's just a number. So let's get a feel for what it could mean. Okay, so let's take two sets of data for weighting at a bank. This is Jefferson Valley Bank. This is Bank of Providence. Now these dots, this is a dot plot. These are the dots that represent the time that they wait. On a single line, you get into a single queue, and as the tellers are available, you get to go. Now this set of data varies less because it's a single wait line. They vary from somewhere to about 6.5 minutes to about 7.8 minutes. The average and the mean and all that are the same, about 7.15. But at Providence, multiple wait lines, you can pick the queue, the line, and then sometimes you'll get lucky, and or you'll calculate that this line's probably quicker. And this person got lucky and waited about 4.3 minutes. This one about 5.4 minutes, and this person got unlucky. These people got unlucky. This person waited about 10 minutes. Now, if we calculate the standard deviation for both of these, this standard deviation is 0.48, and this standard deviation is 1.82. This has more variation, more spread than this one, and that's reflected in the number. The lower the standard deviation, the less spread, and the higher the standard deviation, the higher the spread. Okay, so that makes sense. The bigger the number, the more spread out it is, because it's a measure of the spread of the set of data. But it still doesn't mean too much to us, so let's get some meaning to it. The way we can get meaning to the standard deviation is through the empirical rule or Chebyshev's theorem. Now the empirical rule applies to normal set of data or bell-shaped data, and it centers about the mean, x bar. And it states that about 68% of the data is within one standard deviation of the mean. So you go x bar plus or minus one standard deviation, and you get about 68% of the data. About 95% of the data is within two standard deviations of the mean. So you go x bar plus 2 standard deviations and x bar minus 2 standard deviations, and you get about, that's the operable word, about 95% of the data within 2 standard deviations. And almost all of it, about 99.7% of the data are within 3 standard deviations. So you often hear a 68, 95, 99.7 rule, and that's the empirical rule. Within 3 standard deviations, x bar plus 1, 2, 3 standard deviations, and x bar minus 1, minus 2, minus 3 standard deviations contain about 99.7% of the data. Okay, let's look at an example. And in this example, we have this credit card debt. Okay, and let's see. The mean of the credit card debt is about, it's right here, it's about 750, and the standard deviation is about 300. Okay, now these numbers over here basically correspond, they really should be shifted over. These numbers correspond to right here. Okay, and this one goes to here, this one goes to here, this one goes to here. The zero is really right here. 150 here, 300 here, and so on and so forth. So the mean is really right about here. That's where it looks like it would balance at 750. Okay, so that's the mean. Now if we take the mean plus or minus 1 standard deviation, so 750 minus 300 goes to 450, and 750 plus 300 goes to 1050. That's about 68% of the data. That's about 68% of the data. Now if we go another standard deviation, another 300 down to 150, and up from 1050 to 1350, it's 2 standard deviations. That contains all this here. That contains about 95%. Doesn't it look like it? Okay, and then if we take 3 standard deviations, it would go all the way to 0, and all the way past this, we'd get all of it, which is about 99.7% of the data. So if it's about bell-shaped, mound-shaped, that's what would happen. Okay. So let's do a couple other examples, just to get the empirical rule down. So SAT scores have a mean of 100 and a standard deviation of about a mean of 1,000 and a standard deviation of about 200, and it is about normally distributed. So what percent of scores lie within 600 and 1400 of SAT scores? Well, how many standard deviations is that away? You take 200 from 1,000, so you go to 1,000, 200, 1,000, 400. That's 2 standard deviations down to 800, 600, 2 standard deviations. So about 95% of the data is of people get scores between 600 and 1400. Okay, what range of scores contain 68% of the data? Well, 68% of the data is in the empirical rule is 1 standard deviation. So we take 1,000 plus or minus 200. So that's from 800 to 1,200. Okay, so the empirical rule applies to normal set of data, and it's about. Empirical means experimental, so they observe it to be about that much. Now, what happens if we have a non-normal set of data? A lot of data is not normally distributed. So then we use Chebyshev's, and this applies to any set of data with any distribution. Okay, and the proportion or fraction of any set of data lying within z standard deviations of the mean is always at least 1 minus z squared, where this should be z. Okay, this should be z. Let's make that a z, where z is any positive number greater than 1. Okay, so we have here then, okay, well, if what happens if z is equal to 2 here? If z is equal to 2, then 1 minus 1 over 2 squared is equal to 1 minus 1/4, which is 3/4, so which is equal to 75%. So at least, and that's the operable word, at least 75% of all values lie within 2 standard deviations of the mean, guaranteed no matter what. What about if z is 3 standard deviations away from the mean? Well, if z is equal to 3, then 1 minus 1 over z squared is equal to 1 minus 1 over 3 squared, which is equal to 1 minus 1/9, which is equal to 8/9. Okay, and that's basically 89%, 0.89. So at least 89% of the data lies within 3 standard deviations of the mean, and so on and so forth, and that's guaranteed no matter what. In any universe, in any physics, under any economic rules, under any God, under any belief, it's guaranteed no matter what. It's a proven fact, and there's no free will about it. So guaranteed at least 89% of the values are within 3 standard deviations. So let's have a look at that. Suppose you took a test, and I reported to you that the average was 78 with a standard deviation of 5. That's all you knew. Well, you don't know if it's normally distributed, so you have to use Chebyshev's theorem. So what percent, okay, what percent of scores lie between 68 and 88? Well, 68 and 88, how far is that? Well, how far is that? Well, 88 minus 78, right, is 10, and that's 2 standard deviations, 2 5s away from that. And same with 68, it's 10 units away from 78. So it's 2 standard deviations away from the mean. So Chebyshev says at least 75% of people got a score between 68 and 88, guaranteed, at least. If it's normally distributed, it's more like around 95%, empirical rule. But Chebyshev's at least guaranteed, no matter what, at least 75% of them have scores between 68 and 88. What range contains at least 89%? Well, 3 standard deviations. So x bar plus or minus 3 standard deviations is 15. So from 63 to 93. 63 to 93. Okay, has at least 89%, 3 standard deviations. What about this interval? From 58 to 98. Well, that's 20, right? 78's right in the middle. That's 20 plus and 20 minus. So it's 4 standard deviations, 4 5s. So 4 standard deviations. So 4 standard deviations at least, and at least 1 minus 1 over 4 squared, so it's 1/16. So at least 93.75%, there should be a 5. 93.75% of the data lies in this interval. So just knowing the mean, just knowing the mean of 78 and a standard deviation of 5, you know you're guaranteed that at least 94% of the data lies between 58 and 98, and you know all this other stuff. So that's the interpretation of standard deviation. I gave you a mean and a standard deviation, that's it, and you know all this. So that's pretty cool. Okay. The next thing is z-scores, measures of relative standing. It's like a percentile. Okay. It's like a percentile. And you know what a percentile is? A percentile is, you know, for example, say you got 78 percentile on the GMAT score. That meant that you did better than 78% of the people, and 22% did better than you. We know what percentiles mean. Now z-scores, we can use our knowledge of standard deviation to have a measure of position, and that's what a z-score is. A z-score, or standard score, whenever you hear a standard value, that means a z-score, is a measure of position, and is the number of standard deviations that the data point is away from the mean. So the number of standard deviations that the data value is away from the mean. Okay, so how do we calculate that? Well, we have to get the distance away from the mean. If x is our score, then we have to get the distance away from the mean, x minus x bar, and divided by s to get the number of s's in that. So the number of standard deviations at this value is away from the mean, exactly the way it looks. And this is for a population. Mu is a population mean, sigma is a population standard deviation. Greek symbols are for populations, Latin symbols are for samples. Okay, let's do a couple of examples. Z-scores. So again, if our mean and standard deviation for a set of exam scores was 80 and 5 respectively, what is the z-score for the following test scores? Say you got a 90, a 75, or an 88. What are the z-scores? Okay, well for 90, right, how far is that away from 80? 10. How many 5s are in 10? 2. So it's 2 standard deviations away from the mean, right? Makes sense? 90 is 2 5s, 2 standard deviations away from the mean. What about 75? Well, that's 5 away from the mean, but on the small side. So that z-score is -1. Minus 5 away divided by 5 is -1. So negative z-scores means it's lower than the mean. And 88, right? 88 is just 8 units away from the mean, divided by the standard deviation gives you 1.6. Okay. And then finally, what about for this set of data? What's the z-score for 42? How would you do that? Okay, well, you have to use your calculator. So let's turn this on. All right. Let's turn this on. Okay. So you hit stats and edit, enter. And there's some data in there, so I'll say clear, enter. And I put my data in there. Let's see, we have 29. And we have 31. And we have 33, 36, 38, 41, and 42. Enter. Now we do stats, calculate, so we move over one variable, stats. It assumes list L1, so I'll just hit enter. And our mean was 35.7. And our standard deviation is 4.96. Okay. So let's remember those. Standard deviation is 4.96 and 35.7. Now let's calculate the standard deviation, or the z-score. So let's see. Okay, so all right, so our z-score, z is equal to x minus x bar over s, which is equal to 42 minus 30, what was it? 35.7, okay. 35.7 divided by, I didn't remember it. Divided by 4.96, right? Divided by 4.96. Now we put that in the calculator, and let's go ahead and do that. Let's go to the calculator. Okay, so we hit clear, and we say 42 minus 35.7, enter, divided by 4.96, enter, and there's our z-score, 1.27. So we get 1.27. And there we have it. I hope those examples are useful.